Section 3 deals with massive dark matter. Let's recap the evidence for dark matter that we are already aware of. The most important part is the actual measurement of the cosmic microwave background, which we've been discussing in the previous section, where we found that the angular power spectrum is dominated by a series of acoustic peaks, which indicate that the matter composition is dominated by dark matter, and only a small fraction of the cosmic dust, or that is pressureless matter, is actually in the form of baryonic matter participating in the oscillation. Structure formation then indicates that the dominant form is this non-baryonic dark matter is then the dominant form, which leads to the growth of structures as we see them today. And so the cosmic chart, or cosmic pie as it's often drawn, indicates that we are living in a universe which contains as the dominant form of energy something which behaves like a cosmological constant, which makes up about 70% of the overall energy budget, and 25% roughly is the content in the form of non-baryonic dark matter, and the remaining 4% plus some other stuff is in the form of baryons. And the breakdown of the baryons then is also in the form of free hydrogen, helium, which dominates, and then you have some part which is in the form of stars. Then you've got some heavy elements, and you also have a very tiny fraction in like neutron stars and black holes, and a very small part of the energy is also in the form of neutrinos. Now the structure formation that we discussed in the last section actually indicates that we can be more specific of the type of dark matter, that it is has to be cold in a sense that it does not move relativistically at the time of structure formation, but has a very small streaming velocity, so that structure growth at small scales is not so heavily suppressed as it is the case in for hot dark matter, that is relativistic dark matter, where the streaming horizon is so big that all the small-scale structures are washed away. And this can be nicely demonstrated by these kind of simulations, which we also learned about in the last section, that is N-body simulations, where you basically start with some initial fluctuation spectrum and then you let it evolve due to gravitational stabilities. And depending upon the streaming velocity of the dark matter particle, you end up with characteristic structures as they form. And from left to right in this picture here now, you see on the left column something which would form if the matter that you consider to be non-baryonic is cold, that is massive. And then in the middle and in the right panel you would see something where the energy or the rest mass is so small that these particles would remain relativistic for a large part of the eras of structure formation, and therefore small-scale structures are washed away because these light relativistic particles cannot form deep potential wells, but they sort of stream out of these wells, and they cannot be much structure at small scales. Now the favored concordance cosmology that we've seen here now is describing our universe surprisingly well, is that we have the sum of all the matter forms, that is baryonic matter, dark matter, and dark energy. They come out to be 1, whereas the deviation from 1 is smaller than like a per mil roundabout. And we also find that the baryonic matter is much smaller than the dark matter. And this is then characterized by something which has to be sufficiently massive, at least in most scenarios, to be non-relativistic, and it has to be therefore pressureless, and it has to be electrically neutral. Otherwise, it would have participated in the oscillations during the CMB or prior to the CMB decoupling, and also it should not have disturbed at all the Big Bang nucleosynthesis, where any additional degree of freedom comes in and could potentially harm the way that the nuclei were forming. Now, this is all we know from the early universe, which is already quite compelling. But the important question to look at is what's been carried over in the sort of recent or recent past of our universe, that is our current universe. And so if we look at today's universe, we can again look at indications for dark matter, and there the situation is surprisingly complex. I mean, in the previous case, all we need to know is there's a certain amount of dark matter, it's got to be pressureless, and it's got to be non-relativistic, and so on and so forth. Now, the way that structures form it seems like the dark matter would be playing slightly different roles in the different objects that we are looking at, which is a bit surprising in a sense that it's maybe not expected. Now let's look at the various evidences, and I'm just going to go through that quickly and try to summarize the thing along the way. So we have a large part of our evidence coming from dynamical observations or dynamics of objects, and I call this the dynamical evidence. And among those, then, in different masses, we find the following situation. So we have something which we call dwarf galaxies. These are galaxies which are gravitationally bound to a host galaxy, like, for example, our spiral galaxy has several tens of dwarf galaxies living in the galactic halo, and these galaxies would be, in terms of its luminosity, rather dim, so they would have a similar luminosity as globular clusters, 10 to the 5 solar luminosities. However, if you measure the velocity of these of the stars in these systems, which basically are, they are living in a volume with a characteristic radius of typically a kiloparsec or so, and then what we measure is the velocity velocity dispersion, or the variance of the velocity of these stars. I just indicate that here as an average of v squared as a function of r. And then it turns out that the mass of these systems is typically 10 to the 7 to 10 to the 8 solar masses, which then combined with the luminosity from the visible stars turns out to give a huge mass to light ratio. So that's characterizing this. That's of the order of 10 to the 2 to 10 to the 3 solar masses per solar luminosities. That means that there's about a factor 100 to a few hundred, maybe even up to 1,000 more mass in terms of gravitational mass present than what is visible in terms of luminous matter. And these dwarf galaxies have the interesting characteristics that they are made up only of stars. So there's very little, no gas, no dust left. So there's not anything really that we could hide in terms of, let's say, a cold gas or anything that we could not see maybe. So dwarf galaxies are extremely dark matter dominated, and they're at the lower mass end. If you now go slightly smaller masses, like for example globular clusters, which have about 10 to the 5 solar masses, the massive ones, it turns out the mass to luminosity ratio is pretty much unity, so they don't have any dark matter at all. This is kind of an interesting story by itself. Then we go to the spiral galaxies, like our own galaxy. And similar holds true for elliptical galaxies, but spiral galaxies have this particularly interesting feature, that is that their rotation is ordered. All the stars move around in the same direction. They really have orbits where you then measure a characteristic orbital velocity as a function of the radius. And so this I call the star as a function of r. And this follows a surprising shape. So these rotational curves supposedly should turn down. We'll have a look at some of the data later on. And as a matter of fact, they stay flat, so the rotation velocity remains constant beyond a certain radius, and that's indicative of a hidden halo mass. And so here the mass to luminosity ratio is well below 10. That's typically the upper range. Values like in our galaxies are between 2 to 5. Some of them are a little bit more dark matter dominated, but there's still more mass, more matter present than there is luminous matter. And finally, and these objects, they have masses of 10 to the 11, 10 to the 12, 10 to the 10, so let's say 10 to the 12 solar masses. And that's much more massive than the dwarf galaxies, but however the mass to luminous ratio drops. And then finally we come to the galaxy clusters, which is the next step up in terms of the mass that we're looking at. And here now we are not looking at the velocity of stars anymore, because they are bound in galaxies. We are rather looking at the velocity of whole galaxies. So we measure again a velocity dispersion of galaxies in these systems as a function of distance, and then again we can infer the amount of matter present to keep the objects, in this case galaxies, gravitationally bound. And this turns out to be giving us then something of the order of mass to luminosity ratio of about a few hundred. These are typical values. And for galaxy clusters, we have a second way of measuring the total mass, and that is related to the fact that the intra-cluster medium, that is the dilute gas between the galaxies, turns out to be very hot, tens of millions of degrees Kelvin, and this hot gas emits emission, or has an emission which is characteristic for its temperature, so we can use this X-ray emission coming out of the cluster gas as a thermometer by, for example, measuring emission line strength and also the shape of the spectrum to some extent, but it's mainly the emission lines as a matter of fact, which depend very crucially on the ionization state of the atoms, and therefore the temperature can be determined from that quite accurately. And then you can use the argument that since this gas is gravitationally bound, the kinetic energy of the gas, the pressure of the gas, has to be balanced by the gravitational inpull, and then again you can infer the total mass of the system, and there you get similar values coming from the temperature from this equilibrium state, so the hot intra-cluster gas gives consistent results, and we'll look at that in a moment a bit more detail. Then the next way that we can measure the mass of the system, again through gravitational interaction, is the gravitational lensing. And this is used in various contexts, so this is really a broad field, but there's maybe broadly speaking, two different approaches. So one is that, as we learned, there's a secondary effect, that is that the cosmic microwave background radiation suffers or is deflected in the gravitational potential of the galaxies, and this leads to some changes in the power spectrum that you can be used to reconstruct the power spectrum then again of the intervening matter. And so the CMB provides us the light that can be deflected, and then we can measure at high values of L the deviations, and that's used to determine the dark matter distribution and overall. And then there is the particularly useful measurement of gravitational lens effects of a galaxy cluster in the foreground. So there's a background galaxy. The light is deflected by the gravitational potential of the total cluster, and that's strong lensing effect that allows us to measure the total mass of the system. And then there's the small scale slight shear of this background light, or the shape of galaxies that we see lensed through the matter distribution in the galaxy cluster, and that allows us to infer actually the density distribution of the dark matter in such galaxy clusters. So that is again used to infer, for example, total mass and mass distribution, and that is giving us a very similar number as in the case of measuring velocity dispersion as well as the hot intracluster gas. So these evidences of dark matter that we find are observational, and they are based upon observations on very different mass scales, and they point towards the presence of dark matter in these various systems to be dominating. I gave one exception, that's the globular clusters. And the behavior that we see is that this dark matter component which is present is only visible through gravitational interaction. So we don't have any other means of detecting it so far. And so this is always constrained to be gravitational interaction. The picture that we get has some controversial aspects to it, which I'm not going to be going into great detail, but there is essentially some issues which relate to the way that the dark matter distribution, specifically on small scales, seem to be. For example, in the Dwarf Galaxies, where we probe the dark matter distribution over a length scale of a sub-kiloparsec, there it turns out that the dark matter in the central part of these objects seem to be less concentrated than expected. and also the number of dwarf galaxies that are observed is quite small in comparison to the actual expectation. So let's go through some of these points in a little bit more detail in a moment before we look at some of these observations in detail. Let's just make up a quick list of the things that we know that dark matter is not. So we know it is not baryonic. So it's neither protons or nuclei or whatever, because this clearly is known from the BBN and CMB observations. We know it has to be cold and pressureless. This follows from CMB and structure formation. We know that it is neutral. It doesn't participate in strong interaction. At most, it can interact weakly, but it does not participate in any other form of interaction, just gravitation. And so this way it would not disturb the CMB as such, it would not disturb the Big Bang nucleosynthesis, and it needs to be created in the right amount. So that it basically cannot be overproduced, it cannot be overabundant by very, very much. It's within a factor of few of the baryon energy density, which doesn't naturally have to be like this. It can be in many models, but not in all of them. And of course, it has to be stable in order to survive from the time at which it was present in the CMB formation, as well as until today. So that means that it has to be having a lifetime of sort of a Hubble H timescale. And as a matter of fact, with the measurement of the galaxy clusters, since we know how many galaxy clusters are around, we can infer the total energy density of dark matter in the universe. And it turns out that that number is very well matched with the number that we got from the CMB measurement. So that means that most of the dark matter that was present at CMB time is still around. Now let's look at some of the measurements, observations, I should say. So rotational curves, I just got here one example to demonstrate the point. And so here's a rotation curve, and yellow measured as a function of the distance to the center. And so this is the visual picture of a galaxy. It's not a very nice picture, but it's a spiral galaxy. It's not easily seen. It's M33. And then the stellar rotation that you measure from the central part starts out with maybe 20-30 kilometers per second, and then it rises. And this follows roughly also the distribution of stars in the disk. And then, however, it starts to even rise once you get beyond the core part of this galaxy, so that you don't see many stars anymore. So there's obviously not so much matter anymore. And while you would expect from the visible matter that this curve gradually turns over and then starts dropping with increasing distance, it keeps on rising over here. And so if you just do the math behind this, you would get that the rotational velocity as a function of r, if you just have a completely spherically symmetric mass distribution, would be given by the square root, in a very simple-minded way, calculated just by balancing the forces, for example, would be gm over r, where mass is the mass within the radius r. And if this is constant, what does that mean for the density that you need? That means that m of r needs to be proportional to r. And so once you calculate m of r, this will be then just the integral from 0 to r, let's say 4 pi dr prime r prime squared times the rho of r prime, assuming spherical symmetry for simplicity. And then you see that in order to make this proportional to r, this means that the rho of r, has to be going roughly with 1 over r squared. Okay, so that means that the density increases quickly, but it doesn't drop off very, very quickly, and it actually has to drop off at some point faster than 1 over r squared. Otherwise, you basically would have a divergent total mass. But in this range over here, it should be going roughly with 1 over r squared, and maybe even slightly less steep. And in the central part, We have mostly baryons here, but this is really also a critical issue that we will return to once we talk about indirect dark matter searches, what to expect in the central part of this mass density. And let's go for the dwarf galaxies. Let me just give you some impression of what these beasts look like, and they are really faint. So these are just sky image. Oops, sorry, that's the wrong picture. I got here a nice compilation of actual frames which are taken with telescope pointing at various of these dwarf galaxies. And so this is the sort of set of classical dwarf galaxies. There's in the meantime some additional ones which have been observed. And on most of these frames, with the just with the impression you get, you do not really see anything particular. You do see with some of these cases like Leo 2 and Fornax and Leo 1, you see some sort of nebulosity over here. And this is just individual stars, which however are so few and they are spread out over such a large volume that they do not appear to be much brighter than what you get in terms of the foreground stars that you see along the line of sight. So they are really faint, they're difficult to pick out unless you do dedicated surveys, and then you do some additional studies of the distribution of the color diagrams, and you try to pick them out against the foreground stars. And so it's kind of a difficult story to do this kind of study and discover them. And then once you've got them discovered, you have to go ahead and take spectra, and the spectra are then allowing you to measure the velocity dispersion. That is, you do not measure individual spectra, but you basically look at all the stars at a given radius, and then you measure their velocity distribution through the lines that you get. And so this is just an example of these kind of stellar systems, and they are very similar. So what's plotted here is the sigma v, which is proportional to something like this. So this is the square root of the velocity variance, and these are now plotted as a function of radius, and this is parsec, so this is about a kiloparsec distance here, and you see these systems are basically roughly visible for about a kiloparsec, and the velocity stays constant, and the expectation would be this dashed line here, and you see that the actual observation is well above this, and that's a clear indication that there must be more matter around than what is visible through the stars. So in this case you would expect, for example, a velocity dispersion of 2 or 3 kilometers per second, but the measured value is close to 10, and it remains flat over a large range of radii, which means that this mass distribution that's invisible has to be extending well beyond the part of the galaxy which is traced out by the stars. And these objects are actually quite consistent with, well, to some extent consistent with the expectation. So these n-body simulations that we discussed in the last section give us a clear view on how these dark matter halos would form. They would form through multiple merging event, and in the process of merging you're also left behind with many sub-halo objects which are gravitationally bound, and ultimately will also merge with other objects. But at the given time that we observe them, we would expect many of these kind of sub-halo objects, which presumably are formed out of mostly dark matter. And then in these regions you would also have stars forming, and then there should be some of these dwarf galaxies around. The actual observation of these dwarf galaxies distributed in the galactic halo is shown on the left, and you see that these dwarf galaxies extend in a large halo, which is about several tens of kiloparsecs, up to 50 kiloparsecs roundabout, extended beyond the Milky Way galaxy in the center. And if you look roughly on the same scale in this Quaria simulation and body simulation, you'd expect all of these blue things here to be also sub-halo objects, which could turn out to be dwarf galaxies. And there is a little bit of a tension here between the number of dwarf galaxies that we do observe with the number of sub-halo objects, even though this tends to be getting more and more resolved by, for example, taking into account observational biases and so on and so forth. But this is still something which is under some debate. So that these objects, the dwarf galaxies, they would be the most dark matter dominated objects in the universe, because they would, if you believe these numbers, tend to have a mass to light ratio which is about a few hundred to maybe even 1,000. Let's turn for a moment our attention to galaxy clusters. in a little bit more detail. So the way that we determine the mass of galaxy clusters is by looking at the velocity dispersion of galaxies, and we assume that these galaxies are virialized in the gravitational potential. And this implies that we can say that the twice the average kinetic energy has to be equal to the potential energy, according to Virial's theorem. And if you do then the maths, I'm going to skip that here, you get an estimate of the mass, which is 3 pi over 2 g r sigma v squared. So that's the velocity dispersion. And in handy units, so this is 1.1 times 10 to the 15 solar masses for a velocity dispersion of about 1,000 kilometers per second, and with a radius of a megaparsec of the cluster. So that's the scale that we observed. These are typically masses of 10 to the 15 solar masses, which then you can compare readily with the luminous mass. And that's typically, or let's say the luminosity of these galaxy clusters is about 10 to the 13 solar luminosities. And then you get the mass over light ratio is then of the order of a few hundred solar masses over solar luminosities. And the good thing about galaxy clusters is that we can use also the X-ray observations to check this. So let's have a look at the X-ray observations. So there we have a hot gas in equilibrium, in hydrodynamic equilibrium, or hydrostatic, I should say. And that gives you, that's basically expressed in this equation. That is the divergence of the pressure is given by, or the gradient of the pressure is given by the gradient of the gravitational potential times the density. And using that, we end up with a mass that we can infer, which is roughly proportional to the temperature. So if you have a temperature factor 2, then the mass is 2 times as big, and this radius squared. And then you've got here something. This is the average mass number, which for ionized gas would be around 0.5 if you just have hydrogen in it. And then you get here the gradients of the density which is present and the gradient of the temperature. These are the logarithmic gradients. And this is something which is measurable in the X-ray spectroscopy. And to give you some idea on what this looks like, I give you here now a picture of the Coma Cluster, which is a nearby galaxy cluster, which is very well observed, both in the optical as well as in the X-ray. And so on the left, you see the optical image. There you see now the individual galaxies. These are the yellow galaxies, and often enough, also in Coma, you find giant elliptical galaxies in the center. For the Coma, you find two sort of subclusters, which probably are the result of a merging event. And ultimately, some of these galaxies will merge to form a very massive elliptical galaxy in the center. And then around that, you find all of these galaxies which are gravitationally bound. And then it's possible to measure the spectra in the optical to see what the velocity is. And from that, you get this first measurement of the mass. And the second way, if you turn your X-ray telescope to this galaxy cluster, the actual X-ray emission extends well beyond the optical. So you see this inlay down here, that's the optical image you see from this on the left page, on the left side. And this X-ray emission is picked up between 0.5 and 2 keV. And the intensity is peaked in the central part, and then it drops down a little bit. And by the spectroscopy, it's possible also to measure the temperature of these galaxy clusters. And the temperature that you get is of the order of typically 2 keV and 1 to 2 keV. Now, the last thing which we mentioned about galaxy clusters concerning the gravitational lensing. And here I just want to give you another example, a beautiful picture of a galaxy cluster where you can see the lensing. and the X-ray emission. Oh, sorry, that's the wrong one. Let me pull that in. Got the right picture here. There we go. So this is a galaxy cluster which is observed in the optical. That's the picture where you see all the galaxies. And overlaid in this color scale that is sort of magenta-ish, that's the X-ray emission. And you see nicely that the X-ray emission is centered on the central part with the highest density of galaxies. And this is then, again, a measure of the total mass. There's now several other features I want to point out in this figure. So one is that you see these arcs. These are background galaxies which are lensed through the gravitational lensing, deflection of the gravitational potential of this galaxy cluster. And you see these are partial arcs, but they do have the same radii. So you can see this is a very beautiful arc, and you see some arcs over here. And these can be then used to infer the total mass in this part, which comes down to, again, 10 to the 15 solar masses. And the next point that you can infer is that also you find some background galaxies background galaxies which are lensed in a slightly less strong way. You see that there's some kind of statistical shear and deformation of the background images, and that can then be used to infer the actual mass distribution in a study, which is more or less a statistical study and requires very careful imaging of this thing. Now, the sort of front page type picture that is often shown in this context is the so-called bullet cluster, which brings together various observations. Let's walk through this figure for a moment. So that's again galaxy clusters. Now this is 2 galaxy clusters. You find one cluster of galaxies here, and you find another cluster of galaxies over here, and they are moving in directions. So this one is moving to the left, and this one is moving to the right. So they've been passing through each other. Since the galaxy density is so small, the actual galaxies do not collide. And so there's not much happening. There's some tidal forces acting on the galaxies maybe, but this doesn't really destroy any of these galaxies. So they can pass through each other without being gravitationally bound if the velocity is too large. So in this case, the relative velocity is several thousand kilometers per second, which is larger than the escape velocity, so that the system afterwards does not remain in a bounded state. And then the gravitational lensing, that is the lensing of individual galaxies, can be used to trace the amount of dark matter in this cluster, and that's the blue halo that you see here. And you find that the blue halo is pretty much centered on the distribution of galaxies, so they do not seem to be following any kind of different distribution. And in red overlaid on this is the X-ray emission. And while the dark matter is collisionless and the galaxies are collisionless because they are not interacting so much, the baryonic gas in the intercluster medium is, however, shock heated because the two gaseous components, they pass through each other with a velocity which is larger than the sound velocity in each one of these gas distributions, and this leads to shock heating. And then as a result of the shock heating, the temperature is increased, and then the brightness gets increased. And these are these red conical emission regions which you find from the X-rays. And you note that these are displaced as a matter of fact, because the baryonic component this gas is ionized, and so the long-range Coulomb forces, even though there's no direct collision, leads to some drag in this fluid that you can describe this with. And so this is a compelling type of observational system, because you find that the dark matter distribution and the baryons, the hot gas, do not follow the same kind of behavior, which means that they are really different forms of matter which are present in these systems, and the galaxies are moving with the dominant form of the matter in this system. That is the dark matter, which is visible through the gravitational lenses.